Okay. Professor El-Ghazaly is an assistant professor in the Department of Electrical and Computer Engineering at Cornell University, and also an NSF Career Award recipient. Her work combines magnetism and ferroelectricity to create tunable, versatile electronic systems for telecommunications, sensing, and actuation. Uh, Prior to joining Cornell in 2019, she was a postdoctoral research fellow at the University of California, Berkeley, where she was awarded the University of California President's Postdoctoral Fellowship in 2017. Her postdoctoral research explored new possibilities for ultra-fast, all electrical switching of magnetic nanodots for faster and more efficient computer memories. She earned a PhD in electrical engineering from Stanford University, where she was funded both by the NSF and NDSEG on Graduate Research Fellowship, as well as the Stanford DARE Fellowship until her graduation in 2016. Her PhD research focused on radio frequency devices using magnetic and magnetoelectric thin film composites for tunable wireless communications. She received her bachelor's and master's degrees in electrical and computer engineering from Carnegie Mellon University in 2011. So without further ado, let's hear from Professor El-Ghazaly.
Thank you for this. So long story short, what the introduction is supposed to say is that my life is about magnets and continues to be about magnets. So that's what I'll try to convince you all, that magnets are so wonderful today. Most of today's talk will be about how we make and control and manipulate magnets at the nanoscale. But before we dive deep down in terms of dimensions, I wanted to first give a big overview picture of what our work is about. So I think we're all quite familiar with these electronics that have become indispensable for us in terms of the way that they are so versatile. We can take notes, make calls, search the web on them anytime, anywhere. In my opinion, they've also become a bit of a pain because I can't get away from them, but that's kind of beside the point. Our work in my research group, or at least some aspects of our work, are focused on trying to make these even more versatile. So we focus on trying to make the touch screens more intuitive and provide them with haptic capabilities, and make the communications able to communicate to Wi-Fi, Bluetooth, cellular, GPS, all of that at the same time and in a much more compact form factor. So I'll start with most of the presentation today will be on the haptic project, but then we'll talk a little bit about the communications work at the end, if time allows. So what do we mean by haptic displays or haptic interfaces? And I think the first thing I want to impress upon you is that when you use a touchscreen display, the interaction is mostly just visual. So if you see a keypad on the screen, then you're just pressing what you recognize. But I think it would be a lot more intuitive if the screen itself not only provided a visual interface, but also a tactile interface. So the screen would reconfigure itself if you're touching, if it's displaying a keypad, it would actually deform and produce a keypad interface for you to interact with in a tactile manner. Or if it changes and provides a topographical map or roads of some sort, then it would deform and provide that also. All of this is a very grand vision, and to produce it, though, you have to go deep into the material and device control. We are trying to approach this magnetically, so it would be an orthogonal approach to what the electronics are already using. So if everything is electronically driven, the display is optically displayed, or the image is optically displayed, then we should control the mechanics magnetically. And our work is on creating both the magnetic material that would deform in this display, as well as the electrical control or the magnetic control for that display. The biggest challenge, though, is that if you want to have a tactile interface, you need two almost incompatible objectives. So The first is that the display has to be quite elastic, or the material has to be very, very elastic so that it can deform significantly and you can actually interface with it. And so at the material level, this means low stiffness, high elasticity in order to be able to stretch that much. But at the same time, if you want to interact with a display and actually feel it, not just like have something that's squishy, then it has to apply a large force against your hand. So now it needs to be stiff. So how do we design a material or an interface that has both of these completely contradictory objectives? That's what we've been focusing on for a number of years. And the first thing that comes to mind when people think of like how do you design an actuator that produces a large force is that these are large metallic systems or linear actuators, pistons in a car, or something that is metal and moving, or these motors that are in large factories. Those are the objects that produce large forces. But if you scale it down, if you look inside the metal and think of what exactly is providing that strength, it's as a result of the micro and nanostructured grains that are inside. If it's coming from the grains that are at the micro and nanoscale, then that means that we can scale down the actuators as well and still maintain the strength, because the strength is coming from something even smaller. So if we make a millimeter scale actuator, it'll still be strong because that strength is coming from these micro nanoscale features. So that strength should still be there at smaller scale. And others have been trying to scale these down using some similar objects to what I just showed, like a metallic mechanical actuator that is driven by motors. You can also scale down these types of actuators by making them into thermal, to use temperature change as a mechanism for reconfiguring phase change materials. You can also use ultrasonic or pneumatics with gases. And I think our greatest competitor, the mechanism most similar to our work would be electrical, using dielectric elastomers. So if you have an elastomer that's a dielectric and you put a couple plates across it, apply a very, very large electric field, like in the kilovolts range, it will compress and stretch. There are obviously major drawbacks to that approach, and we try to mitigate them by making magnetic elastomers. So these are rubber materials that have magnetic materials embedded inside, and then we can deform them with a magnetic field and create that actuation that we want. But coming back to the question of force, so again, I said if we scale down a mechanical system, a metallic mechanical system, they should be able to maintain that force that it generates by simply maintaining the mass. So it does not fracture because of those micro and nanostructured grains. It maintains that structure when you scale it down. So if we try to apply the same logic, what exactly is the feature in magnetic materials that when we scale it down, we need to be able to maintain? So taking a look at a similar actuator, it's the magnetic properties that are inside of the actuator itself that respond to the magnetic field. So force on a magnetic material is the magnetic moment time dotted with the gradient. So if there's a magnetic field applied and there's a gradient in that field, as long as we can scale down the material and still maintain the magnetic moment, then it should be able to scale, still apply a large actuation force at much smaller scales. So a lot of today's talk will focus on how do we make these materials, how do we provide the material with a strong magnetic moment, and then I'll show some actuator prototypes that we've also developed. Starting with the magnetic elastomer films, though, we have a quick summary of what has been done in the literature so far. And the first thing that you notice is these are the volume fraction, so how many particles have been put inside as a function of particle size. And most of the work is with particles that are in the micrometer range, but very few are in the nanoscale range. When it comes to actually making a tactile display or something that can provide you with high resolution surfaces that can effectively represent like texture, ripples of the skin. These need to be using, these need to have really tight radii of curvature. And so therefore the material that's embedded inside needs to be very small. So our work will tend to focus on the nanoscale, but there's a reason why most of the work has been done in the microscale. That's just simply because most of the materials that you can get commercially are microparticles, as well as the fact that it's very easy to have high magnetization within a microparticle, because you don't have like edge effects that you would get from nanoparticles. So they tend to be, I guess, have better magnetic fidelity in the material. But there are also consequences to magnetic microparticles as opposed to nanoparticles, and that's that what I'll show later is that they tend to be multi-domain, so they don't have their uniform magnetization throughout the material, but they can be easily magnetized. And because they have a larger mass, that means that generally when you try to apply a magnetic field, they have more inertia. So it'll take more magnetic field to move the same to move the same film if it has microparticles in it versus if it has something much smaller like nanoparticles. And then the drawback of nanoparticles is if you scale them too small, then they become thermally unstable and you lose all of your magnetic magnetization in general. So we approached our research by exploring both and comparing both, and I'll show you kind of the trade-offs of each of those. We bought just commercial microparticles and nanoparticles, and then later developed our own magnetic materials as well. So just to prove the behavior of these two materials, I'll first show what has been the standard in literature. So when people take iron magnetic microparticles, so these are 4 to 8 microns in diameter, they mix them into elastomer, make sure it's very well mixed. Then we put it in some sort of mold to take the form and make sure to degas it. In the very last step, we can either cure it in a magnetic field so that the film becomes what we call anisotropic, so the magnetic particles chain up, or the film becomes isotropic. So if there's no magnetic field, the magnetic particles are randomly distributed in the film. And the response to a magnetic field, the actuation response to a magnetic field is very different for each of the two films. So this is just a quick SEM image showing that we were able to achieve those isotropic and anisotropic arrangements of the particles in the elastomer films. And then the actual deflection comparison comes from a setup that we built in the lab. If we mount our magnetic material on this surface and then apply a magnetic field just simply by moving the magnet closer, then the film will deflect and we can focus on the surface to determine the amount of deflection that was achieved. So what's being applied here is actually the magnetic field gradient. As I said, the force is related to the gradient, but a lot of times it's easier to discuss just the field. So here we plot the comparison of isotropic versus anisotropic deflection. And it's very clear that one of the two wins out. So this is for films with just 6% by volume of magnetic particles in the film. And we already get out of a 200 micron thick film millimeter scale deflection. So 2000 microns is just 2 millimeters deflection at fairly low fields. And what we're interested in is actually these fields that are 100 millitesla or below that are fairly easy to apply within an electronic system. So we did the same comparison with nanoparticles. These are 40 to 60 nanometers in diameter, and made isotropic versus anisotropic films with both, and then compared them as a function of volume percent, and also looked at how much deflection happens at the small field range. But the interesting thing that we'll see here is, if you remember what I said about the main difference between microparticles and nanoparticles is how much can you actually produce, how much deflection can you produce in a low magnetic field? So microparticles, because of their larger mass, they're going to have a lot more inertia. So it's quite likely that these nanoparticles are able to deform more than the microparticles. And so if we compare just the same volume concentration of each directly, then you can see that. So the microparticles are the ones that are in blue, and the nanoparticles are in red. And if we just apply a really small magnetic field, the nanoparticle films immediately start to deflect, and we even get 3/4 of a millimeter deflection in just 100 millitesla field range. And then for the anisotropic films, their deflection is larger than the microparticle films at all fields.
Well, do you want questions along the way or?
Sure, yeah, you can break.
So, just want to make sure I understood the mechanism that causes the deflection. Is it just the twisting of the domains that kind of stretches the elastomer and causes deflection, or is there like force being created between the particles? What is actually causing the deflection?
Yeah, so there are two mechanisms that we're trying to compare here. The reason, well, let me first describe the anisotropic one, because that's the easiest. Originally, what we want is that the anisotropic films, if they're all chained up properly, then you reinforce the magnetization. So these are interacting magnetic particles, and you have a larger magnetic moment along that direction. So we increase the magnetic moment, and then that should respond more to a gradient and deflect towards a field. But then also it's responsive to an orthogonal magnetic field. So the one equation I didn't show is torque is M cross B. So if I apply a magnetic field orthogonal, then this high magnetization chain is going to bend. And then that'll force the entire film to bump up. So with the anisotropic films, hopefully if they maintain a strong magnetization or magnetic moment, we would be able to win in both of those cases. In the isotropic films, if they're randomly distributed, then you can't really guarantee that the coupling between them is going to reinforce the magnetization. They will probably cancel. We have a lot more details in our paper about why the isotropic one tends to deform more overall in this case, but yeah, I'll kind of not talk about that now. But in the isotropic case, you have kind of like an overall averaging of the particles that reduces your net moment, but then at the same time, these ones will only be responsive to a field gradient. So once the field magnetizes the particles, then they'll move towards the field. But then if you apply an orthogonal field, it's still very random in orientation. And so then if there's no reason for them to torque, and then if the field is strong enough for them to magnetize, they'll magnetize along the field. And then now there's no reason for it to torque. The magnetization is parallel to the magnetic field. Does that fully answer your question? There's a lot going on.
Based on what you said, I would have thought that anisotropic would deflect
Should
more.
to perform better, yes.
But your data says otherwise, right?
Yes, so I can go into a lot more detail.
That's fine,
I have,
that's
like,
fine.
some background.
Yeah, but
The main reason is because these are soft magnetic particles, and we're not getting the increase in actually, I think I have the magnetization here later. Yeah, so I don't think I included the description of why these are better, but the mechanism here is force and not torque. So it depends on how easily are each of these magnetized in the field and how much do they deflect. And
that's fine.
yeah, there's a lot more. I think one of the interesting things that we found though in these materials is also like, why is it that the nanoparticles, if we back up a bit, in the beginning of the talk, I said, okay, nanoparticles, they have a bunch of edge effects, so they lose their magnetization at the edges. Also, when you scale it down, they tend to have a lower magnetic moment if they're randomized due to thermal fluctuations. In this case, our nanoparticles are actually deflecting more than the microparticles. So that must mean that the magnetization is better in some way. So if you look back at the magnetization curves, overall, what you see is that if you apply a large enough field, kind of the effect that I said is true. So the nanoparticles, because of the loss of magnetization at the edges, and the surface to volume ratio, these ones do have a net lower magnetization than the microparticles, but the true reason for their better performance is this tiny little section here. If you spread it out, the nanoparticles have what we call higher remnant magnetization or higher magnetic moment when there's no field applied. So this is the feature that we want to keep improving in the nanoparticles. And like how much do they actually maintain, how well do they actually maintain the magnetization as they're scaled down and as they're as no magnetic field is applied. And everything, again, like I said, we're trying to focus on fields that are below 100 millitesla because that's easily applied within an integrated system. So coming back to this picture, we compared the two, and it seems that the nanoparticle ones are better, so we can move in this direction. But kind of addressing the issue of like, how do we get that better magnetic coupling between the particles? We first look at whether or not we're getting the ideal chaining behavior. So like I kind of in answering Professor Hrudi's question, like how do we get a higher net magnetization in a given axis? The magnetic particles need to be coupled so that one is applying a field on the other, and then overall we get a higher remnant magnetization. But when you look at these films, it's not perfect chaining. It does look like there's agglomeration in certain regions. Whereas the ideal case would be like one particle wide chains. It's not the case. So if you start looking at where those agglomerations are, like you'll easily start to find fault in these films very quickly. But if you increase what you find is if you increase the nanoparticle concentration in the films, that agglomeration just dramatically increases. And so the best way to improve this is by somehow making particles that are not so strongly interacting with each other. The particles that we're using are iron nanoparticles that have no surface coating. So they once mixed into the material, they're interacting very closely with their nearest neighbor, and that strong dipole interaction reduces the net magnetization. So if these want to align anti-parallel so that the flux can go from one to the other one, then the net magnetization in this direction would be effectively zero. But if you mix that into the film, then and you still have these agglomerations, then in the end, that moment that I was saying that's going to improve our actuation, that is now reduced. So one way to improve this is if you functionalize the surfaces and have these longer ligands that separate the particles. So then the interaction is weaker, and when we apply an external field to align it, they can actually respond to the magnetic field and align properly, and then we should get nice cleaner chains. So this is some work that we did in collaboration with Professor Lyndon Archer's group in chemical engineering. So they attached ligands to our iron nanoparticles and finished that off with PDMS so that it can mix well into our elastomers. And then to compare all of them together, if the magnetic moment the content is the same, then the magnetization, which is the density of the magnetic moment, should also kind of be the same and scale as a function of volume. So if we increase the volume linearly, this data point here, the triangle is the only one that is coated with the ligands. We ended up getting a 2.7% by volume concentration. So all of them fit in a linear trend, but then so the green one is the one that's coated with ligands. But then if you look at how much magnetization do you actually get in that direction, the one that's coated with the ligands is much, much higher. So we did show that, just simply coating with ligands and separating them initially when you mix it into the elastomer, that allows them to better align in the magnetic field and gives you a net magnetic moment that's higher than what we were getting in all other cases. And this is great. So hopefully we can align these better and then see a difference in the deflection, and we did. So the one to pay attention to here is the green one that's coated with the ligands. And in comparison, all the other ones were the ones we previously saw. So the different volume concentrations of magnetic particles without the functionalization. So the green one just passes everybody and wins the race in the force dominated deflection regime. And coming back to kind of like the anisotropy question. So when we align the particles, I said that these should also be very responsive to an orthogonal field and should torque. So we can also do bending experiments. In this case, we apply a field orthogonal to the direction of those magnetic moments. And here, again, the ones that are better aligned, so those particles that have the ligands on them get a higher bending angle regardless of the volume concentration, or the regardless of the field applied. But this is all still with commercial nanoparticles, and I said that a lot of our work in our group is with making our own materials. So these are the curves of the just typical magnetic iron oxide magnetic particles that are used in the literature, and you can see what the magnetic moment is for that. And iron, both of these have a very low remnant magnetization. So one thing that we try to do is improve the nanoparticle composition itself and increase its remnant magnetization. And that's where I'll get to the second portion of my talk. So how do we actually increase the performance that you get from a single magnetic nanoparticle or a single magnetic nanostructure? And there are two ways. Again, what we're interested in is how do we increase this data point? So at zero applied magnetic field, it still maintains as much magnetic moment as it can. This can be done in either two ways. You can either just completely shift the curve upward, like stretch it larger by increasing the saturation magnetization. And theoretically, this curve is well known in the field of magnetism as the Slater-Pauling curve. It compares the room temperature magnetic compositions that you can get from iron, cobalt, and nickel, which are the three magnetic elements at room temperature. And the highest magnetization is for iron, cobalt, iron 65, cobalt 35. So we can do that. That's one way. And then we also can try to stretch this curve wider to get a higher coercivity and therefore like lift this point up just by stretching the curve. So the way to increase the coercivity is by making the material single domain. In other words, there's just one net magnetic magnetization within the material and no other sections with opposite magnetization. If you compare coercivity as a function of particle size, though, this becomes quite a challenging thing to do. So at very small particle sizes, your particles become super paramagnetic. So what I said is they're thermally unstable. Their magnetization is rotating as a function of time, and it's hard to track down. But if you increase it, you'll get to that single domain sweet spot. But if you just make the particles just a little bit larger, then all of a sudden they want to cancel that magnetization on themselves, and the magnetization starts to curl and then eventually break up into multi-domain. So in this multi-domain case, there's net, again, zero magnetization because the different magnetization regions are canceling. So we ideally want this behavior, but the problem with increasing saturation magnetization, which was the first approach, and going towards this iron cobalt, is that as you increase the amount of magnetization that you can get in a material, the critical radius for achieving this single domain just drops significantly. So you have an even narrower range of dimensions where you can achieve the best performance. despite all of this, we still tried to go for it, perhaps naively, but it seems to have worked. So my student Yulan Chen synthesized iron cobalt nanoparticles and developed a process to get a very good dispersion, so uniform distribution of these nanoparticles in size, and also a crystalline nature to them. So they have a cubic structure in the end once they're synthesized, and you can see that the structure of the nanocube is very is well ordered. Once you remove the cube from the synthesis, then it oxidizes at the surface. So we do confirm that there's like a spinel shell, but the main part of the nanoparticle is just purely iron cobalt. And my student then compared the nanoparticles as a function of size so that we can try to identify that narrow range of particle sizes where we can get single domain behavior. If you look at simulations of the material properties, it's a very small range of sizes. So 1620 nanometers based on simulation should be uniform magnetization. Anything higher than that, and the magnetization starts to curl upon itself and become multi-domain. This is a comparison of both experiments and simulations. So the curves on the right are the experimental behavior. You can see that the remnants is higher for 17 and 34 nanometers. These are the particles that, the two smallest particle sizes that she synthesized. The one for 34 nanometers, we still thought it was going to start curling on itself, but it seems to have fairly high remnants still. And then any higher and it becomes multi-domain. You see the sudden drop in the remnant magnetization to near zero. So already just based on the single nanoparticle size, we can increase the remnant magnetization significantly compared to commercial nanoparticles, but we can still do better. So obviously there's still a lot left here on the table that we're not using. There's a huge portion of the magnetization that that still remains to be had at zero field. And one way to improve that is by reducing what we call the shape anisotropy, or increasing the shape anisotropy and reducing the demagnetization field. So we can go from just a single particle to then a nano chain and get a higher remnant magnetization. Most of the ways people synthesize these is just applying a magnetic field during synthesis, and then the particles will align within the field. In our case, though, our particles are so strongly magnetic that we don't need to apply an external field. They just self-align and self-assemble into nano chains during the synthesis process. So if you synthesize a sufficient concentration of these particles within the solution, they'll be able to find each other and form spontaneously form a self-assembled nanochain that is well connected. So these are not chains that once you remove the field, they'll break apart again. They're pretty much growing onto each other. And these ended up giving us the best performance so far. So if you just compare like the random orientation of the particles versus nanochains, we already see an improvement in the remnant magnetization for the nanochains. But then if you actually align all of the nanochains in a magnetic field, and you can see how big of a difference that is. So the aligned ones are the ones in red, and the remnant magnetization is quite large compared to the random or orthogonal magnetization. The only problem with these particle chains so far is that we're still, again, not getting like 100% of the magnetization. And that's because the particles are, when we ended up making the chains, they also not only grew in length, they grew in width, and they're no longer single domain. We have some, if you simulate it, we do have some flux closure inside the nano chain. So the next step is to try to make these not only chains, but also single domain nano chains and hopefully increase that further. Nevertheless, my student tried to optimize this and make it into an actuator just to show its performance. So she measured the net composition, the net magnetization of the composite if you vary the concentration of these. So again, if you make them really high in concentration and really packed in, they're going to couple magnetically to each other and effectively reduce the net magnetization, just like they would in a multi-domain material. But if they're low concentration, then you have low magnetization just simply because there's a lower amount of magnetic content. So if you vary the amount of magnetic material, you actually get a higher sweet spot of magnetization, remnant magnetization of the composite at a 6% volume concentration. And that also corresponds to the largest coercivity within the film. And both of these correspond to also what we theoretically calculate as the ideal composition. So without further ado, let me show you some fun videos of like what the students did. Our goal is if we want to increase both force and elasticity, then some regions within the material are going to be the ones that have the magnetic particles. So those, by putting magnetic particles into the elastomer, it stiffens the elastomer. So these can be the ones that regions that contribute the force to the overall material. But then the rest of the material is just pure elastomer, no magnetic composition, no magnetic content, and then that should provide larger deflection. So Yulan made these films where there are nanoparticle chains aligned vertically. This is a cross-section image of those chains within the film. And then she put them into a composite. So the magnetic particle films are only in 2 panels, and the rest is non-magnetic elastomer. And then she stuck it onto an aluminum plate, like you can see here on the right. In this first demo, she just wanted to show what are the various configurations in which the material can move. So if you magnetize them both parallel and rotate it, the magnetization crossed with the magnetic field will produce a torque on both sides that gives you like this S shape. And then if you, of course, move it closer to one side, then it'll bend uniformly. And if they both if they're oppositely magnetized and experience an orthogonal field, then they'll bend upwards in the same direction. So this was promising, as it meant that even though she only had, again, 6 volume% of the particles in this tiny little film, it was able to produce a lot of deflection. But it's still quite thick and it's not integrated in an actuator. So we can consider how to, without going in too much into detail of the theory, we can consider how to make this even better. The main thing is that if you want to look at the elastic energy, the biggest contributor is how thick is your material. So the moment of inertia is related to the thickness. If we reduce the thickness, we'll get a significantly larger amount of deflection. And that's where we went to. So another student used the iron particles just to show how much deflection these would experience if you apply magnetic fields locally and deflect it. But again, these are the iron particles, so they're soft magnetic. And actually, I might just this is the comparison I think that you were asking for earlier. Like, what does the particle arrangement, how does that affect the torques and forces? I don't want to go too much into detail here, but the main advantage that we get from using hard magnetic particles or high moment particles like Yulan produced and anisotropic ones is that you have both large force response and large torque. And so one way to just prove this while continuing to improve our iron cobalt nanoparticle performance, one way to just demonstrate that we can achieve large actuation is to prove the mechanical motion with commercial hard magnetic particles and then go back to our nanoparticles later. So right now, we did some experiments with neodymium iron boron particles that are 5 micron in diameter. And you can see that the remnants compared to our own synthesized particles is quite a bit higher, but I think our particles can get there. But you can see here that the difference is going to be quite strong. So if we start with a material on a table that is completely misaligned with the magnetic field, it'll rotate just when experiences the magnetic field, it'll completely rotate 90 degrees despite all of the friction that's present. So we formed magnetic haptic taxels, tactile pixel of these with the magnetization either oriented up or down. So if they are oppositely oriented and you apply an in-plane magnetic field, they'll each torque towards the field and bend the film upward. And then I think we'll skip this one as well. We also made a control frame. So if the magnetizations in the two regions on the left and right are magnetized anti-parallel to each other, and the sample is placed in the middle, then the sample experiences no magnetic field. But then when you flip one of the magnetizations just by applying a current to it, then now these anti-parallel magnetization sections produce field that is forced to return through the center region. And this is a demo that my student produced a few weeks ago, where you can see the large deflection when one of the magnetizations, when that same magnetization is switched, and the sample up on top either is in the on or off state. The biggest problem with this, I guess, right now is the energy is quite large, and the amount of current and field is very large. But theoretically, with magnets, as long as we can scale down the dimensions of the system and the time, we can apply a very fast pulse, we should be able to switch within nanosecond time scale. So these magnetic materials, if we switched it in nanoseconds, the energy would still remain the same, but the amount of power consumed would significantly reduce. Okay, so for the first part of the talk, I just wanted to show the magnetic materials that we have, the magnetic elastomers that we've compared, and the magnetic materials that we are working on, have produced, and are continuing to work on to get different actuations. And we're continuing to try to scale these down and produce larger amounts of deflection. With a little bit of time remaining, I also wanted to talk about some materials that we're producing for communications. So the goal of this work is to try to shrink down the systems for wireless communication. So right now, if you have cellular, GPS, Wi-Fi or Bluetooth communications or anything else, each module has a separate integrated circuit on board. But what we'd like to do is make this a lot more compact. So merge a lot of the filtering into just single sets of filters or components that are then tunable and are tunable magnetically. To make this possible, we're both exploring the materials themselves, and specifically high anisotropy materials that can operate at high frequencies for wireless communications, and also the integrated components that would be tunable. So, so far, most of our work is on the materials, and I'll just talk a little bit about how we're trying to get them into the 3 to 30 gigahertz range or possibly above. So far, if you compare what has been done in the wireless spectrum magnetically, all of the magnetic devices are operating below like 3 gigahertz or below what is called the ferromagnetic resonance of a material. If it's below that resonance frequency, then you get a large permeability. But as soon as you try to operate the magnetic material above the resonance frequency, then all of a sudden it becomes a lot more lossy. So what people do instead is just simply forego the magnetic material and just make an air core device or inductor of sorts. And our goal is to keep the magnetic material in by, instead of using the typical metallic ferromagnets that have a resonance frequency of 3 gigahertz or below, or around the single digit gigahertz and below, we're switching to other types of materials. So ferrimagnets and antiferromagnets have higher resonance frequencies, and would therefore give us a larger bandwidth of operation that we can use. So the one consequence of switching to other types of materials, though, is that there is a direct trade-off. As you increase the resonance frequency, the permeability will decrease. So the amount of the contribution that the magnetic material can provide to the system also goes down. We're aiming primarily in the 10 to 30 gigahertz frequency range for now for the new devices that are in for 5G and 6G electronics. And the first approach is to use a synthetic antiferromagnet. So this is using conventional ferromagnets that are easy to grow, easy to characterize, but you just couple them with a thin film of a non-magnetic metal. So in this case, ruthenium. And as long as that thin film is optimized, then depending on its thickness, it'll either go as you change the ruthenium thickness, it'll either go between ferromagnetic or antiferromagnetic coupling between these two films. So we can optimize the thickness to get a very strong anti-parallel or antiferromagnetic interaction, which pushes the resonance frequency higher. And this has been shown in the literature already. In our case, we did this optimization by varying both the ruthenium thickness as well as the cobalt iron boron thickness. So if the magnetic material also grows, then the effect of the interface on that magnetic material is reduced. So there's a certain trade-off that happens as a function of magnetic material thickness and ruthenium interlayers, basically. Yes. When we grow each of these, we have to extract the exchange and anisotropy parameters. So I'm just going to show a quick comparison of the two. So if you just grow a single cobalt iron boron thickness, you get a typical ferromagnetic loop. And that gives you the saturation magnetization and the anisotropy field that would be typical of magnetic material. But then as soon as they're coupled with ruthenium interlayer, then all of a sudden you get these more unique curves where there's an exchange interaction that shifts the curve, shifts the kink over and increases the amount of energy stored in the system. And then when you increase the energy, you also increase the bandwidth. So we can optimize these and get at this point, so for our initial films only produced a resonance frequency of 6.2 gigahertz, but anything higher than that, it's possible that we would see other complications as well. So this initial film did increase the bandwidth of iron cobalt to an antiferromagnet, but not as much as we wanted. So we also looked into ferri magnets. During my postdoc, I had worked on gadolinium cobalt and observed that it switched ultra fast when we excite it with a laser pulse. And each of these switching behaviors, which you can see from the contrast change, that happens within the picosecond time scale. What was unique though is after years of trying to understand like how do we grow and optimize this material, what we found is that this ultra fast behavior and the high bandwidth only worked if the material was slightly oxidized by accident in the lab. It would only, if it was oxidized, it would work. So coming here to Cornell, we started trying to actually control this and understand how much oxidation is needed to improve the anisotropy. So first we grew, you can co-sputter gadolinium and cobalt onto a film and vary the concentration of each of those elements, and then observe what is the anisotropy or the energy in the material, as well as what the magnetization, how much magnetization you see. So in a ferri magnet, there's a certain temperature at which the two moments will perfectly cancel and you get zero net magnetization. We call that the compensation temperature. You can also get a compensation when the magnetic content is if gadolinium and cobalt are what we call sublattices that are oppositely magnetized, if each one is contributing a certain amount of magnetization, as we vary the composition, we should get to a certain composition where the two are oppositely magnetized and equal in content, so there's no net magnetization. And that's observed if you see this graph where we plot the saturation magnetization as a function of gadolinium content. There's a certain point at which the magnetization drops to 0. That same composition, just to either the left or the right of it, is where the anisotropy suddenly shoots up. So we wanted to operate just either to the left or to the right. We chose to operate at a 35, gadolinium 35, cobalt 55, 65, sorry. And then we can actually, and then we measured the anisotropy to actually compare the two and determine which one has the highest anisotropy and therefore the highest bandwidth. And you can see that the gadolinium 35 cobalt 65 has the highest anisotropy. That could have been enough, but we decided to go a little bit, I'm gonna skip the compensation temperature. We decided to also try to improve the anisotropy further, and you can get anisotropy both from the material, but also from coupling and magnetization strength through shape. So, oh, sorry, that's the next one. As I mentioned, we saw high anisotropy in my postdoc because of oxidation. So we also varied the oxygen content as a function of flow rate during the growth and optimize the peak at which we see largest amount of anisotropy energy. The reason for why oxygen is improving the anisotropy is due to what we call in magnetism super exchange. So if you look at the different interactions of all the elements within the film, is either gadolinium is interacting with gadolinium, or gadolinium is interacting with cobalt, cobalt with cobalt, or any of these mediated through an oxygen sitting in between. In this case, when there's an oxygen sitting in between, that's where we see super exchange, and the strongest interactions were found to be only the gadolinium cobalt, the initial antiferromagnetic interaction, as well as the gadolinium oxygen cobalt and cobalt oxygen cobalt. So in the end, we can simplify, we can understand the material and try to increase the antiferromagnetic interaction of this gadolinium oxygen cobalt interaction by optimizing the oxygen concentration within the film. So with all of this, we get that the majority of the film if the majority of the film is oxidized, we can get a huge amount, a huge increase in the effective anisotropy. I think I'll finish this up and end here. So then we can stack the films on top of each other and increase the anisotropy further. With 10 layers of this stack, you get an anisotropy field of about 11 kiloersteds, which corresponds to a bandwidth of 30 gigahertz. With that, we are working on also integrated components, which would be tunable. The idea behind that would be to put a certain magnetic material that we've now designed and grown with the optimal ferromagnetic resonance frequency onto a piezoelectric, and then control the piezoelectric with voltage to strain the system. And that strain would couple to the magnetic material and change its resonance frequency and behavior. So these are some prior demonstrations from my previous work, and I'll kind of leave it at that. Okay. Many thanks to my research group, and sorry for taking all the time. So I'm happy to answer any questions.
I have one question. So when you, is there any benefit to using maybe nano rods instead of trying to chain up particles and just get rods themselves, like something where Professor Julie Child also.
Yeah, so rods would be better because you get more control over the the shape and the structure, of course, and therefore the alignment. But the problem is that nanorods, well, there are two problems. Nanorods, usually they, to make the nanorods, you have to use a template and either electroplate or use some other deposition system to get it. And we're really particular about wanting to use this specific composition, so it's not something that's easily electroplated. The other issue is that with a templated growth, you have a low yield. And if we want to use this for an application instead of just a material study, then we need to increase the amount of nanorods that are produced. So we can't do just that templated growth of nanorods.
Thank you. Is there any other question?
It's a very naive question, but you said in electronic devices, it's pretty easy to apply fields less than 100 millitesla or something. How do you practically do that in devices? Is it just some current flow or?
That's actually a really good question, not a naive question. So we plan to use other magnets as well to produce the field. So we have some work where you look at the coupling between two magnets. And then that way you can, actually long story short, that no matter how much you try, if you pump a lot of current into just an electromagnet of the same size as a magnet, it's very hard to get the same field unless you're driving like tens or hundreds of amps through an electromagnet. So to produce a field within an electronic system, we're looking at just using magnetic material to produce the field, but then to switch the magnetic materials magnetization by driving a quick current. So you can either, our current design is you can either have one magnetic material that's magnetized up and another material that's magnetized in plane. And then the coupling between these, just from the in plane one to the out of plane one, the field would go from its north to the other one's south, so underneath. But if I flip the magnetization of the out of plane one, then all of a sudden the coupling goes up above. So I can control how much, let's say, a film is experiencing by simply switching one of the magnets, and it can be current driven switching with a lot lower current than what's required to produce that field initially.
Got it. Thanks.
I guess just to add to that, in addition to the fact that you need more current, you also have to continuously drive that current.
Yes,
which means you have much more losses.
Yeah.
So this way you can latch and kind of do essentially what an electrostatic can do, which is charge up and then install it.
Yeah, I forgot to mention that. That was the main reason why we're also designing this, the electropermanent magnet controls. So these ones, almost there. Yes. So these ones, they're called electropermanent magnets because you can produce the field almost as a permanent magnetic field once it's been switched. So we're basically trying to do the same thing at the micro scale. All you have to do is consider the dynamic power or the dynamic current required to switch the magnetization, but then once it has been switched, your static power, the operating power is 0.
I not for this application, but for sort of as a soft magnet, some of these nanoparticles and I guess and the difference between the anisotropic and isotropic. How do the hysteresis curve, the width of the hysteresis curve or the area within the hysteresis curve compare between anisotropic and isotropic at the nanoparticle? So if I were just wanting to make very nice soft magnets, soft magnetic material.
Okay.
So I want like the hysteretic loop area to be really tiny.
Mm-hmm.
Not for this application. Is there a difference that you see between just the inherent hysteretic loss in the two type of materials? Where you had the pH curves there, but it was hard to tell which one had bigger hysteretic loss?
So I think, let me do that one real quick. Can't remember which one it was. I think it's. Yeah, you're saying this case, the softest cases were the
The red one seems,
permalloy, the.
yeah, the red one seems to be pretty soft,
Mm-hmm.
compared to the dashed ones. But actually, I think if you go back to earlier slides, you don't have to do it now, but you had some really zoomed in versions where you could actually tell the difference. And I'm just curious at some point.
Yeah, so the difference between the soft or hard, it all comes down to this, so the hysteresis all comes down to what I've been describing as coercivity. So what we've been trying to do is actually the opposite of what you're trying to do. So we've been trying to increase the coercivity so that we can like increase the width of this curve and therefore increase the remnants.
But I mean, to first order, it comes to coercivity, unless you can shape it so that it has high coercivity, but then just drops really rapidly after that. Right, because from a loss perspective, I don't care whether it's high coercivity or not, but I do want the area to be small. So the blue curve would be fine, but then the slope is too low. So I'd rather, once it goes negative, just flips.
Oh.
Because the loss is just the area within that BH loop. So as long as the BH loop is narrow, I'm not really concerned about the coercivity.
So if I understand you correctly, you're saying like you don't mind the worst case scenario of like a really wide curve, but just as long as it's very steep.
Yeah.
But then are you not considering the?
Yeah, but also narrow. But doesn't have, so you care about the vertical dimension, right? You care where that intercept is on top and bottom.
Yes, yeah.
And I'm saying, leave that intercept there, but just shrink them. So that as soon as you go, your applied field is a little negative, all the domains flip.
Okay, yeah.
And so your coercivity is still there, but you flip rapidly, so you don't have this sort of linear decline, but rather like that orange curve or really sharp decline.
So if you make a material like this with what I mean
give
by
it some width so that it's not.
okay, yeah, so
yeah, that would be the ideal.
Right.
I mean, that would be good. I mean, I don't really care whether it's that or just. So that area is all that matters, whether it's linear or vertical doesn't matter.
So in our case, so we could also still achieve this if you have a single domain, but as soon as you have a large area material, then what contributes to the width here is the domain, as a lot of times the domain walls. So if this material, the neodymium iron boron, like if we just simply draw it as like multi-domains, then as you're trying to magnetize it, what is making it require a large field, or what is making it magnetize here is that when the magnetic field is applied, this domain wall has to shift so that more of the material is magnetized. But there are pinning sites that resist the shifting, resist the magnetization, and then force it to wait until a larger field is applied and then magnetize it. So
if you had sort of those ligands, or you had sort of some oxide, something so that those domains weren't right next to one another, then maybe you could flip them more easily. Anyway, doesn't matter. I mean, just like this is more of a.
Okay, so you're saying not the continuous film, like in our composites. Like how can you make a soft composite?
Yeah, I mean, because I'm just trying to basically concentrate field. So essentially, if I want to magnify the field, right? So I apply some field and then all these domains turn in the right direction. But I don't want that to be a lossy mechanism, so that when I flip, it just flips with little energy.
Oh, okay.
That's the goal, right? So for applications, for example, where you even a motor, right? If you want a motor, you want lots of flux. But it's going to be constantly changing flux. Or any other application, like an good inductor or a good transformer. So there, you just want the field to get magnified, but not have losses in that as you change the direction of the field. So the domain flipping operation needs to be low dissipative.
Yes.
have Low energy dissipation.
So I think your goal is actually the same as ours. So in our case, the iron cobalt, like as long as it is a single domain, so there are no domain walls, you don't have to deal with the pinning. It'll still have a very steep curve, but what we're right now, what we're trying, like right now, it's not straight. But we want to make it.
The iron cobalt thing looks really good.
Yeah.
The only thing I'm concerned about that is we haven't considered other loss mechanisms, which are like eddy current losses. So if the material is highly conductive, then you have not just this loss, but also, although I presume those losses are accounted for here, because depending on what frequency this was measured at, they may or may not be. So is this at like
This is very low frequency.
very low frequency? Yeah, so if you go to higher frequencies, these curves will further expand potentially, because now you have eddy currents induced in the material, which will also show up on your pH measurement equipment as a widening of this thing. But if for your application, doesn't matter, because you're not gonna flip these at multi-megahertz or gigahertz frequency. You're gonna basically do it as essentially for keyboard application.
Yes,
Order of
yes,
seconds.
exactly.
Okay, thank you, everyone.
Thank you all for staying.
We'll see you again for our next EDS talk.
Yeah.
Okay, thank you.